Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the RSA algorithm for cryptography. Now, I say that it's simplified here because the actual algorithm also involves things like padding, which is when you add on extra data to your message so that it meets a specific format. But we're not going to look at that. We're just going to look at the core component of RSA, which is using modular exponentiation. Now, RSA is a very secure algorithm, but it is computationally expensive. For this reason, if we have to encrypt a large file or a very long message, AES is preferred. But in AES, the key for that needs to be kept secure. So RSA is often employed for key exchange, for actually sending the key to the intended recipient. It's also used for things like digital signatures, which don't require a lot of computational power. So RSA is part of a family known as public key algorithms. So the public key in RSA consists of two numbers, n and e. So n equals pq. Here p and q are primes, so n is a semi-prime number. Optimally, we want p and q to be roughly the same length, same number of digits, and we want them to be distinct. Standard is P and Q will be primes of about 1,024 bits in length, so N will have 2,048 bits. That's an extremely long number. We're talking about a number that, if represented in base 10, would have about 617 digits. Now, the genius behind RSA is that it's easy to multiply together two primes, even if they're 1,024 bits in length. A computer can do that without a lot of trouble. But trying to factorize a 2,048-bit number, particularly one that doesn't have many factors, this one will only have 4 factors, p, q, n, and 1. So that's actually really difficult. At the time of making this, the start of 2026, computers can't handle factorizing an integer that large, though I do note there is some concern that if quantum computing really takes off, it may be able to factorize such integers. And that would mean RSA is no longer secure. Now, also part of the public key is this number e. It needs to be a number that's co-prime to phi of n. So the RSA has this public key, anybody can see it, and that's needed for encryption. Just think if you access like a bank server and you use their key, you need to know this key so that your data can then be encrypted. When you log on to your own accounts, it's encrypted so it can't be hacked. But there's also here this private key, which consists of 3 numbers D, P, and Q. That's kept private. Only the intended recipient knows it. So the idea, even if you know the public key, you can't decrypt unless you have the private key. So in the private key, D is the multiplicative inverse of E modulo phi of n. That's why we need E to be co-prime to phi of n, otherwise it won't have an inverse in that modulus. And then also kept secret is P and Q, the two primes that multiply together to make n. All right, let's now look at exactly how it works. So the first thing we need to do is choose a suitable value of n. So it is the product of two primes. I've just chosen the primes as 73 and 47. So this is my value of n. So now we need to calculate phi of n. That's very easy to do if we know the factors. So it's just p minus 1 times q minus 1, which gives us 3312. Hopefully that gives you the first insight as to the security of RSA. See, when we were doing Euler's totient function, you might remember that phi of n was determined by the factors of n. It's actually really hard to calculate phi of n if you don't know its factors. So that's why knowing P and Q allows us to decrypt, but not knowing them makes it really hard. So next we have to choose a value of e that is co-prime to phi of n. We just need to choose a prime that is not a factor of either of these two numbers. So I'll just choose e equals 97. So now we're going to take our message and convert it to numbers. So when the computer uses this algorithm, it would use the ASC codes and do everything in binary. I just think the algorithm is going to be hard enough to understand, so we're just going to choose the easy method. You can look up this table if you've forgotten. We have B is 01, E is 04, W 22, A is 00, R17, and E again is 04. Now what we want to do is group this in blocks. So we're going to choose the maximum possible block size so that there's no way any block can be greater than n. The block has to always be less than n. Now, if I group in blocks of 4, that means 4 of these digits or 2 letters, the largest possible value it could have is 2525. That would be if it was ZZ. So I can group these in blocks of 4. So we have block size of 4. We're going to operate independently on each of those 3 blocks. What we're going to do to each of them is raise them to the power of e modulo n. So when you're performing each of these calculations, I don't mind if you use Symbolab because it can handle them very easily, but unlike AI, it won't just tell you the whole answer and decrypt the message for you. So putting this into Symbolab, we get 2174, 2782, and we get 231 for the last one. So we'll just put a 0 there so it has 4 digits. So our ciphertext is 217427820231. It will often be displayed in hex. I won't convert it to hex in this video because I think the algorithm is complicated enough. So now what we're going to do is take our ciphertext here and I'll show you how to decrypt it. So here was our ciphertext. We need one more thing in order to decrypt, and that is the value of D, which if you remember was part of the private key. So D is the multiplicative inverse of E modulo phi of n. So to calculate this, you can use Symbolab again. We get 3073. That is the value of D. So the reason RSA works is if we have DE equivalent to 1 modulo phi of n, we can use this rule up here. We know that A to the phi of n plus 1 is always equal to A in modulo n. So raising to this power is like an identity. It doesn't actually do anything to the text. We raised it to the power of e. If we raise it to the power of d now, we'll get back to where we started. Because d and e are inverses of each other, this will always be equivalent to 1 modulo phi of n. So all we have to do is now take this into blocks of 4 again and raise to the power of d. So we can use Symbolab to help us do this. We get 104, 2200, 1704. So now we have back our plain text. It was 0104, 2200, 1704. To convert it back to letters, we just use the table again. So 01 is B, 04 is E, then W-A-R-E. We are back to where we started. So note again, one good thing about this algorithm is that if you have the same letter, it's not mapped to the same number. We saw in the text the first E was mapped to this 74, the second E to 31. That makes frequency analysis almost impossible to do on an algorithm like this. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.